All right, everybody. Welcome back. I got two announcements. One with regards to Chem 101. I know that there's still an issue with the video lag. IST has requested information. I sent an email earlier, and then they said, oh, and could you ask them to do this? So they actually gave me a different website for the speed test, but they're also looking for information about your browser to try to figure out what the issue is with regards to some people seeing very low resolution video, and it's intermittent for some people and it's constant for others. So I would appreciate that if you are experiencing problems, that you just kind of flip over to your email and run the what is my browser, save it or print it as a PDF, and then run the speed test and do the same thing. Remember, the class video is going to be uploaded anyway, so you'll be able to get it there. So that your assistance will help us track down the problem in terms of, is it a browser issue, is it a network connectivity issue, or my money is actually it's a problem with Teams and their inability to handle large volumes of data being transmitted. So if you can do that, that's great. We'll be able to get to the root problem of the cause of this and get it resolved. Much appreciated. Secondly, I came across an article the other day. It came across my desk yesterday, actually. And if you had the opportunity to watch the YouTube video talks about meta learning, it's actually in the folder for the course on YouTube. One of the things that I did talk about in that YouTube video is that exercise is important. Exercise keeps your brain active and engaged, and it helps you process information. The article that came across my desk was, it doesn't take an hour or more of strenuous exercise, just 10 to 15 minutes of exercise is enough to increase the endorphin levels in your body and get you your mind processing much faster. So instead of just kind of sitting around doing nothing for 15 minutes, if you have an opportunity, get out, go for a brisk walk, something like that, just outside fresh air. All of that will help you in terms of learning. All right. To now look at the course material, we ended off here. And we were looking at the method of initial rates, and we were partway through this question. Very specifically, what we had done last day, oops, that's not what I wanted, excuse me, is we had derived this equation as a general combined rate equation, comparing two different runs of the same reaction, and then we applied it to that nitrogen monoxide oxygen reaction that was present there, and by carefully setting up the experiment, we were able to remove any dependence on the product because we produced always the same amount of product, and so that got reduced to 1 in our calculations. And then we compared runs 1 and 2. And again, by going back to the data, we set up the experiment such that runs 1 and 2 had an oxygen concentration that was constant. And with that constant oxygen concentration, it cancels out here, and we were able to, using logarithms, go through and calculate the order of reaction for this with respect to nitrogen monoxide. And we found out that it was second order in nitrogen monoxide. That's where we ended off last day. What we now need to do is we need to calculate the order of reaction with regards to oxygen and the rate constant for that reaction. And so that's what we're going to do now. Now, going back and looking at the data, what we find is that we need to have the oxygen concentration varying. And so if I were to compare runs 1 and 3, that would do that. Or if I compared runs 2 and 3, I would also get the oxygen concentration varying, and I'd be able to calculate the order of reaction with regard to that. I'm going to do runs 1 and 3, If you want to do runs 2 and 3 and confirm for yourself that you're going to get the same value, go right ahead. You don't need to follow what I'm doing. So I'm now going to compare runs 1 and 3. And when we do all of the looking at the data table, we get this. Oops, excuse me. Is equal to 0.015. We end up with that expression plugging in all of the available data. Now, it doesn't matter that the nitrogen monoxide concentration varies because we know that M is equal to 2. So we can just plug that in and life's great. Again, our units cancel throughout all of this, so that's convenient. And when we go through and do the math, you get 0.042 is equal to 0.273 raised to the power of 2 times 0.563 raised to the power of n. And that's a 6. All right, I'm not going to go through and show the basic mathematics to manipulate this, but you're going to do the basic mathematics and you're going to take logs and you're going to find that n rounded to the nearest integer, half integer, is 1. So it is first order in oxygen. So we can now write our rate equation, and what we find is that we have the rate is equal to some rate constant K. I don't know why this keeps moving, but nitrogen monoxide squared times oxygen to the first power. We have the orders of reactions, we have the rate of the reaction, and we have the concentrations of nitrogen monoxide and oxygen. The only thing we don't know is the rate constant K. So I can now go through and solve for K, and that is simply the rate divided by nitrogen monoxide, oxygen. I'll come back to this slide in just a second. We have 3 runs that have been done here. It is a check on your work to make sure you didn't make an error to calculate the rate constant for runs 1, 2, and 3. It should be a constant, so the number shouldn't vary a lot. And so that's exactly what we're going to do. We're going to calculate the rate constant for each of the individual runs and make sure that we haven't made an error somewhere else, because the error would show up with the rate constant changing. Well, as a matter of fact, you're going to do that. I would normally just, apportion the class to do data set for K1, calculate the rate constant for K2, and other group to calculate the rate constant for K3. I'm going to leave it to you to do this and just pick 1, 2, or 3 and plug the numbers into your calculator. We're not going to worry about units right now, but plug the numbers into your calculator and come up with K1, K2, and K3, please. Thank you. And when you're done, just type it into the chat. I do happen to have the ability to see that right now. Or you can speak it out loud. And once we get confirmation with 2 people getting the same value, we're going to assume that that's correct. And your value has to match the number I got. Can I show the numbers? Sure, I can show the numbers. That's there. There's the data. But this means that I'm in the video. You also need to tell me if you'd like me to play the Jeopardy theme music during this period of time. What do people have for numbers? Which one is that, Benjamin? K1, K2, or K3? So Benjamin has K2 is equal to 7182. Anyone else have the same number? Or K1 or K3? So Jada agrees that K2 is 7182. And K3, 7052. And K1, 7078. So there's a lot of people getting K1 is 7078. And we just need confirmation on K3 is 7052. Good deal. So people working together, we got 7052 as the one for K3, the value for K3. We didn't do units, but we can come back up here and we can look at the units. So all of these units happen to be tabulated, but the units of rate were moles per liter second. And of course, the units of concentration are moles per liter squared and moles per liter for nitrogen monoxide and oxygen. This ends up being a complex fraction. Moles per liter cancels, and so that becomes 1 over S is equal to over moles per liter all squared. That's a fairly complex fraction, but it ends up simplifying to liters squared over moles squared seconds. And that is the units that we have here. Liters squared per mole squared seconds for all of them. The other thing is significant digits. If we look at this calculation for K, that's the one up here, okay, everything's multiplication and division. So going back and looking at my data table, what I find is that the rules for propagating significant digits through for multiplication and division are the least number of significant digits get propagated through. And so that is 2 for the data that we have here. So we've kept all of the digits, which is good, which is actually good, but I'm just going to underline, if I can get a color, the insignificant digits, okay? 7078, well, to suit two significant digits, it's just 70. The second one, it's 71 and 70. In terms of your calculations, keep all of the digits that you're given, store them in your calculator's memory or your computer's memory, no problem at all, and we're only going to round the final answer. But if we look at the initial digits, 70, 71, and 70, the number isn't changing. It's not changing with digits that are significant, and so we can be reasonably confident that we've done the calculations right and that these numbers are calculated right. So if we now want to calculate the average, what we get is 7104 liters squared per mole squared seconds. And again, the 0.4 is not significant, but I'm carrying it through my calculation. And this now allows me to write the overall rate equation. V is equal to 7.1 times 10 to the 3 liters squared per mole squared seconds times nitrogen monoxide concentration squared times oxygen concentration. We have something that is second order in nitrogen monoxide, first order in oxygen, and the overall order of reaction is the orders added together. It is third order overall. And the rate constant to the correct number of significant digits is 7.1 times 10 to the 3 with units liters squared per mole squared seconds. And that answers this question. We're able to completely come up with an equation that completely is able to calculate the rate of the reaction as a function of concentration. Does anyone have any questions on that? I would appreciate if you would just use the voice feature. It's a little bit quicker to get questions. And no one knows who you are anyway. All right, so if there aren't any questions, we will continue. This example is similar but different in the sense that there aren't actual concentrations. What we end up having is placeholders. We have an initial concentration that's given the value A1 and B1 and the like. So I'm not going to completely go through this, but I'm going to set it up and get you to calculate the order of reaction. So for this equation, actually I'm just going to go back to that right now. The same thing is true. We do need to get the concentration to be constant somewhere. And if we compare runs 1 and 2, we find out that A is constant in runs 1 and 2. So I'm going to start by comparing runs 1 and 2. So here we've got run 1 over run 2 is equal to, and we had concentration 1. Okay, I'm just going to put in concentration 2 raised to the power of m, B1 over B2 raised to the power of n. So what I would like you to do, we plug this in and we get number 4.1 moles per liter second over 4.0 moles per liter second is equal to You go through and do it. I want you to end up setting this thing up and solving it. So you go through, set this up and solve it, and tell me what the order of reaction is with respect to B. Go for it. Question, Christian? Oh, can I show the numbers? Yes, I can show the numbers. Sorry. What does someone get, or does anyone get, as the order of reaction with respect to B? Someone's got a number that they're willing to share, please. You can start off by saying, I don't know if I'm right, but I got blank. And what you're going to find most likely is that a dozen other people are going to go, hey, I got the same number. And while we're thinking about that, would you prefer it if I put you into breakout rooms and then brought you back so you can actually chat without being engaged with everybody in the classroom? Prefer the breakout rooms. Okay, well, I'll work on that for next day. It won't be today. So, yes, I will do the breakout rooms on your behalf. Did anyone else get 0.667, or did you get different numbers? Now everyone starts putting up an answer. Yes. Okay, if we go through and we do all of this, what we find out is that the order ends up, well, we'll see in a few seconds. So when we plug these things in, no, I need the data sheet. You get, oops, A1 over A1 raised to the power of M. And then we have B1 over 1.5 times B 1 raised to the power of n. In terms of cancellation, of course the units cancel, but a1 cancels, and that makes this entire thing 1, and b1 cancels, and so we're left with 4.1 over 4.0 is equal to 1 over 1.5 raised to the power of n. Okay, and yes, Christian pointed out that solving this, n is equal to negative 0.06, but because we're looking for integer or half integer values, this becomes and what we have is a 0th order reaction. What I would like you to do as a homework exercise is go through and calculate the order with respect to A, and then the overall rate of this reaction, the rate constant, of this reaction, and bring that back for Monday's class. And we will just at the very beginning quickly go through the numbers. So that's an exercise for you to take home and do. We're going to go and continue with this. And to start with, we're going to move into the idea of integrated rate equations and then look at another way to determine the order of reaction. So we have an analytical equation is a mathematical function that gives the state of a system under arbitrary conditions. So the state of the system is anything you want to know about it. The concentration, the pressures, the temperatures, that type of idea. And an analytical equation, you just plug in concentration, temperature, pressures, whatever, you get a value. You get the state of that system. So if I were to go back over to this example here, what we find out is that that rate equation is an analytical expression. I put in whatever concentrations I have for nitrogen monoxide and oxygen, and I will get the rate of that reaction. So we calculated there the rate as a function of reactant concentration. What we're going to look at in this section is how to calculate the concentration as a function of time. This is done quite differently than what we did before. We're going to specifically look at the most common orders of reaction, 0th, 1st, and 2nd order reactions, and then from that develop analytical rate expressions for those three. So now a little bit of a backing up right here. Okay, I can do it here. This is not a calculus-based course. However, this is calculus. And so for the students who are taking calculus, I am going to go through and just exemplify that, hey, calculus does actually have applications by doing these integrations. It's not testable. I will tell you when you can open your eyes if you haven't taken calculus before. But I do want to go through and do these for the benefit of the people that are taking calculus and going on and continuing on in more mathematical sciences. So we're going to start with a 0th order reaction. And what was just on the previous slide was this expression delta A over, let's try that again, over delta T is equal to minus K. Right? The order of the other reactants, A is to the 0, B is to the 0, and like, so all of that becomes 1, and you're left with delta A over delta T is minus K. That is the differential rate equation. For those of you who aren't taking calculus, now you can close your eyes. For those of you who have math background, calculus backgrounds, the easier way to write this, the more common way to write this is dA dt is minus k. And we can rearrange this to become dA is equal to minus k dt, which we are going to now integrate from 0 to t on both sides. When we do that, this, by the way, is the absolute simplest integration ever. We have a evaluated at t and 0 is equal to minus kt evaluated at t and 0. We do that, you have concentration at time t minus the concentration at time 0 is equal to minus k t minus 0. And after all is said and done, t minus 0 is, of course, just simply t. And rearrange to solve for a at time t is equal to minus kt plus a 0. Now you need to start paying attention because we have now got the integrated rate equation. You don't need to know how to go. Let me just zoom this down a little bit. Quite a bit, apparently. You don't need to know how to go from the differential rate equation to the integrated rate equation, but you need to know that you need to know that they're both applied to 0th order reactions. So that's the integrated rate equation for a 0th order reaction. Some things about this is you might realize that this is actually can be related to the equation of a line. We have y, m, x, and b. So if we were to plot concentration as a function of time versus time, that will give you a linear graph. Concentration as a function of time versus time gets you a linear graph. And now that's going to be a blue pen, not a whatever color pen. We'll actually come back to that in just a few seconds. I want to introduce a new concept. We just derived the integrated rate equation. I want to introduce the concept of half-life. This allows us to give it an intuitive value of how long is this reaction going to take. And we arbitrarily say, how long does it take for half of it to disappear? So the half-life is defined as the time required for half of a reactant to undergo reaction. You do need to know how to derive the half-life equation because that's just simple a mathematical manipulation. It's algebra. So this is the half-life of a 0th order reaction. And so when we are at the half-life, a couple of things exist. By definition, the concentration at time t is half the initial concentration. 1/2 times the initial concentration. And there is a slight units change. T becomes a fixed value given the symbol T1/2. So we're going to take these things and we're going to substitute them in, to that equation right there. And what we get is this. So we end up with A0 over 2 is equal to minus K T1/2 plus the initial concentration. Manipulate that a little bit, and I end up getting excuse me, minus kt1 half is equal to a naught over 2 minus a0. So this is half the concentration minus the original. That becomes negative a0 over 2. It's negative on both sides, so I can just multiply through and get that expression right there. So I end up with kt1 half is equal to a0 over 2, which rearranges to give me t1 half is equal to the concentration, initial concentration, over 2 times the rate constant k. And that is the half-life of a 0th order reaction. That derivation is something that I expect you to be able to do. For given an integrated rate equation, determine the half-life. So what happens when we look at this? I mentioned, or I showed you that concentration versus time was linear. So if we start with an initial concentration, A0, of our reactant, it will decrease linearly to 0 if the reaction is 0th order. Similarly, the product concentration, because it's simply reactants goes to products, will increase linearly to the final value and then be done. The half-life depends on the initial concentration. So if I start at time 0, the half-life is literally half the time to get to 0, but then I go from half to a quarter, and the half-life becomes a quarter, then an eighth, then a 16th. So the half-life goes down as I go from the full unit to half, to a quarter, to an eighth, to a 16th, and the like. So this is the reaction profile for a 0th order reaction. What are some examples of a 0th order reaction? Well, I understand that most of the students that are in this class are under the age of 19, so you've never had the experience of alcohol, but you can take it from, well, I don't drink alcohol either. And this is the time when I really wish I actually had a classroom full of students, because with me making that statement, people are giggling, people are looking away, people are smiling, people are pulling out alcohol. I have no idea what they do. But anyway, back to the example. How your body processes alcohol occurs through a 0th order process. Your liver degrades the alcohol at a rate of about 0.012 and 0.018% per hour. It depends on the individual, depends on your tolerance for alcohol, depends on your experience with alcohol, it depends on your genetics. But you generally have a number that how you degrade alcohol. Actually, the biological degradation by the liver is a catalytic process. The enzymes in the liver are the catalysts. Any catalytic reaction is 0th order in the reactant. You're limited by the catalyst concentration. So if you've ever cut or hurt yourself and you went and you've poured hydrogen peroxide on the wound, it is the iron in your blood that is catalyzing the hydrogen peroxide to decompose and gives you the little bubbling action going on there. That actually doesn't say anything about whether you have an infection or not. It's just saying that there's iron and there's blood there, and once you create the oxygen, that oxygen will kill any organisms if they happen to be there. A little aside. Any reaction involving solids and liquids occurs via a 0th order process because it is limited by the surface area of the interaction zone. So going back to the first example here, the biological degradation of alcohol by the liver, that is actually a challenge question in your problem set 1. You don't have the ability to answer all of problem set 1, but you can do some of them because some of them are on method of initial rates, but the challenge question is literally John and Jane going drinking. They have different body masses, and you can calculate what their blood alcohol is. You can calculate how long it's going to take for them to reach a point where they can drive, to reach a point where the blood alcohol drops down to 0. It's a challenge question because it's very involved. But as of right now, you have the ability to answer that challenge question completely. So feel free to this weekend start looking at problem set 1, start working on at least the challenge question and anything associated with the method of initial rates, because we have that ability. You have that ability. I'm going to carry on and look at a first order reaction. So deriving the integrated rate equation for a first order reaction and deriving the half-life equation for that same first order reaction. I have enough space here. Good. I think I have enough space. First order reaction. Oh. So in a first order reaction, we ended up with, let me just go back to the example here. One of the reactants is to the order of 1. And so now we're left with delta A over delta T is equal to minus K times A. Now, I am going to do the integration associated with this reaction. Again, you don't need to know it. I'm not going to do it for the second order. That's a little bit more involved. But I do want to do this because it does bring up some of the basics that you've learned in your calculus course. So again, if you haven't taken calculus, let's just pretend that the next minute or so doesn't happen. Actually, this is our differential rate equation. And from a calculus perspective, this is simply dA dt is minus Ka, which I can rewrite to be dA over A is minus K dt. And I can integrate both of these from 0 to t. The integration of dA over A happens to be the natural log of A evaluated between 0 and t is equal to minus kt evaluated between 0 and t. And like before, natural log of A t minus the natural log of A 0 is equal to minus k t minus 0. And just to manipulate it to get A of t by itself, natural log of A of t is equal to minus kt plus the natural log of A 0. Okay, we're back in for everybody. This is the integrated rate equation. This is also in a linear form, y, mx, and b. And so by plotting the natural log of concentration versus time, that is linear. The next thing I want to do is I just want to realize that and point out to you that there are actually two forms of this integrated rate equation. This happens to be the log form. Okay, that's the natural log form of the integrated rate equation. There's also an exponential form. So if I take this equation, I'm going to work on getting an integrated version of it. And so to rearrange this a little bit, natural log of a of t minus natural log of a 0 is minus kt. Okay. Math time. If I have natural log of a minus the natural log of b, how can I simplify that, please? What is the simplification for natural log of a minus the natural log of b? Anyone? It's not natural log of a minus b. Nope. Natural log of a over b. Yes. So this simplifies to the natural log of a over b. So here we have natural log a of t over a 0 is equal to minus kt. And now what I want to do is I want to take e to everything. Everything is taken up as an exponential. Back to math trivia time. That's okay, Kaylin. I won't hold it against you. Math trivia time, sorry. E to the natural log of a. How does that simplify? E to the natural log of a simplifies to, anyone? Avery, a. Those are inverse operations, so they cancel each other out. So if I go back and I apply that over here, I end up with a of t over a 0 is equal to minus kt. Or rewritten ever so slightly, a of t is equal to a 0. Oh, my bad. E to the minus kt. I applied that to everything. E to the minus kt minus kt. That is another form of the integrated rate equation. So these two are the same equation. One just happens to be the natural log form. The other happens to be the exponential form of the integrated rate equation for a first order reaction. I'm just going to zoom in on the bottom half so you can write it down if you missed out on that. Given the time, that actually is it for today. So does anyone have any questions before we conclude? Someone raised their hand and I didn't see who it was, so please let me go to a participant list. Yeah, that doesn't help. Avery, you have a question? Go ahead.
I just wanted to say about the connectivity issues. I was having really bad problems and then I downloaded the app today instead of going straight from the web browser, and like everything worked perfectly. So I don't know if anyone else is still experiencing issues, but maybe try downloading the app and it worked really well.
Excellent, thank you. I will actually pass that on to IT too, because that might be a factor that they need to start telling everybody. Thank you, Avery. Catherine.
I actually had the app downloaded from the beginning and I'm still having connectivity issues.
Okay.
So that might be a solution, but it hasn't been a solution for me.
It's not the solution for everybody, but it will, again, let's see if we can figure this out. I appreciate it. Catherine, we will work through that. Yeah, so like I said, if you have experienced connectivity issues this class, right now, go back, check your email, because I sent you an email about an hour ago, and run those two tests. One is to determine your speed test, and the other one is to get information on your browser. And like I said, I'm forwarding all of this information to IT, and they will be looking at that. I'm actually just going to stop the recording right now.